reconciling different approaches. And the reason we're having this session, very obviously, is the 5 to 6 gigaton difference between emission estimates produced by emission inventories and those used by working group scientists within IPCC, both for historical emissions and for models. And the reason this does all come down to carbon dioxide fluxes from land use change in forestry, and the issue for IPCC was really first identified and worked on in the special report on climate change inland. And just to say why it matters, we are getting a lot of questions from countries still hoping to set net zero targets who want to understand precisely what net zero means. And it is also notable that the UNFCCC synthesis of the NDCs had to take explicit account of the issue in its synthesis report. So it's technical, but it's also very important in terms of policy terms. And just to say right at the beginning, it's not because scientists are making errors or there are mistakes in there. It's down to questions of scope and methodology. And very clever people, like the people on this panel, understand it. The challenge is communicating the issues to a wider audience. So just to start off, there are many important concepts that are named after Italians. We've got the Bernoulli theorem, we've got the Fibonacci sequence, and now this has become known as the Grassi issue. And so the plan of action today is that Giacomo Grassi himself, who's sitting to my right, is going to provide an overall explanation of the problem and the reconciliation. Then we're going to do a deep dive into each of the relevant methodologies, which is the emission inventories, bookkeeping models, dynamic global vegetation models, and integrated assessment models, and the way they approach this topic. Then there will be one presentation once again to pull it all together. The presenters only have 10 minutes, so I'm going to introduce them very briefly at the start of each presentation. And if they're efficient, we can have one question for clarification after each. But first of all, I'm going to straight over to Giacomo Grassi. He's Senior Scientific Officer at the Joint Research Centre of the European Commission at ISPRA, where he leads the group on land use change and forestry. And he was a lead author on the Special Report on Climate Change and Land. So over to you, Giacomo.
Thank you, Jim. Thank you very much for this excellent introduction. Good afternoon to everybody. Well, I was asked to provide an overview of the topic that will be then discussed by each of the speaker. That's true. Does it advance? Okay. Thank you. Well, I will start with the context why the Paris Agreement, the global stocktake, and why land use is so important. Then we'll deep into the problem mentioned by Jim. This large gap on land use fluxes is a gap which raises a number of questions that I will address in my presentation, and you will hear the other discussing that away. Okay. So, the Paris Agreement, I think most of you are familiar with this kind of graph. You see the black line indicate the historical emission from national greenhouse gas inventory, which are increasing. On the right side, the color lines are representative scenarios from integrated assessment models. Essentially, there is a temperature range associated with each scenario of emissions. And as you know, the Paris Agreement aimed to hold global warming to well below 2 degrees, which implies reaching a balance between anthropogenic emissions and removals in the second half of the century. But to make it a bit more lively, let's put the Paris Agreement into a car. And there are 3 actors there. There is the driver, there is the car dashboard, and the navigation system. The driver is like the policymaker. He holds the steering wheel and decides the direction. The car dashboard are like the national greenhouse gas inventory. They provide information to policy and for assessing compliance to the Paris Agreement. The navigation systems are like the global models. And here today you will hear from the other speaker details about 3 categories of global models. There are the bookkeeping models, which address the historical emissions from land use. You have integrated assessment model, which explore future pathway. And then you have the dynamic global vegetation model, which, among other things, estimate the natural sinks. These are like the navigation system because they provide the position, so where we are, and the routes to specific destinations. You see in the image is like that the driver just decided to go in a direction to well below 2 degrees. And when destination is selected, the driver uses the navigation system to check that they are on track. And the same actually happens here in these hours, in these days, with the global stocktake that, as you know, every 5 years assesses the collective progress toward the well below 2 degree target in the light of the best available science. And I think it's very remarkable. And essentially, the inputs that the global stocktake will use are, on the one side, the aggregated country data. On the other side, we'll use IPCC and other scientific data to compare where we are, to assess the future gap, and this would then lead to an increased climate ambitions in the subsequent round of national determined contributions. Why land use is so important? This is a snapshot from the global carbon budget. On the left, you have the anthropogenic emissions, mostly from fossil fuel, but also from land use changes. On the right are where these emissions goes. You know that nearly half remains in the atmosphere, creating global warming, but thanks to ocean and forest, these reservoirs absorb nearly half of global anthropogenic CO2 emissions. You see that forests are particularly crucial because they're on both sides of the equations, both on the deforestation side and on the absorption side. Where the problem is? Well, the problem is that recent studies identify a large gap on land use change fluxes. With land use change, I mean here LULUCF for, as a sector of greenhouse gas inventory, between models and country. In the graph, you see above 2 categories of global models. For the historical period, the bookkeeping models, and then you have various scenarios from the integrated assessment model. As you can see, there is nearly 6 gigatons gap with what countries report in their national inventories for LULUCF, for the historical period and the future. Clearly, this gap may confuse policymakers and raises a number of questions that I will address one by one. First of all, why do we have this gap? Well, it's mostly due to different definitions of anthropogenic sink. Here you have various categories of land and various activities. And global models distinguish anthropogenic and natural fluxes in a way which is fundamentally different from what countries do. Essentially, countries, and we'll have Sandro that will explain it better later, but essentially are based on IPCC guidance and in most cases use direct observation, which do not allow to separate anthropogenic and natural in the same way models do. The two approaches were developed for different scopes. Both are valid in their specific contexts, but the problem is that they are not comparable. Coming back to our friend in the car, often I'm asked, okay, given such a big difference, who is right, who is wrong? Well, this is a wrong question. It's like asking, what is right? Is the car dashboard using kilometer or the navigation system using miles? The problem is that we have a mismatch, different metrics. No one is better than the other. The mistake we should avoid is to compare one to the other. So is this gap a problem? Yes, it is a problem. The graph on the left is the one I showed before. The one on the right is actually the situation we are now. Because of a mismatch in historical period, this mismatch will reflect also in the future. And this will lead to an inaccurate estimation of future gap. Essentially, we are comparing here apple and oranges, but even more, apples and octopus. Essentially, the gap is a problem, and if not addressed, countries' progress may look better than it is. Therefore, the key message is that the global stocktake requires comparability. The other topic is, okay, but can we really trust country LULUCF data? I mean, a recent paper summarized the information coming from countries. Despite the quality can still be improved, there are still a lot of gaps, but the quality actually, the amount of information, the quality improved a lot recently. In this data set just published, we collected information from 186 countries. The missing ones are very minor ones for LULUCF. And a relevant LULUCF LULUCF sink globally is confirmed. Importantly, this paper separates fluxes into 4 categories: forest land deforestation, organic soil, and other, which we propose as a minimum common denominator between the detailed reporting of unsworn countries, the less detailed reporting from developing countries, and the output of global models. So these categories have already been used in the Global Carbon Budget 2022, and the data set has been also used in the UNEP-GAP report. So these categories set the basis for an operational comparison between global models and countries. So the most difficult question is, can we reconcile this difference? So coming to the figure above, essentially another way to explain the problem is that the LULUCF in global models is the box highlighted in orange, while countries consider LULUCF not only the land use changes, but also part of the sink that models consider natural. So the approach that we implemented in scientific studies together with the global carbon budget community is to identify, to quantify in a spatial explicit way the sink that models call natural and countries call anthropogenic. And we added that to what models call anthropogenic, so the orange box. Or it can also be subtracted from inventories. The approach proved to be quite successful as a quick fix to reconciling the 2 categories, so models on one side and inventories on another. Coming back again to our friends, it's like that if we translated the navigation system. There is, of course, the other option to change the car dashboard, but it's far more complicated. It would require changing the IPCC guidance and an FCC decision. It would take much more time, and actually is not even feasible because countries relying on direct observation, which combine the direct anthropogenic effect and the indirect one. We are in Egypt, and what we did is a sort of, we call it a Rosetta Stone. A Rosetta Stone means being able to translate between 2 different languages, and we translated from the language of global models to the one of inventories. Last slide. Got stuck. Okay, the issue has been well acknowledged at the highest level now. As Jim said, it featured in the summary for policymaker of the IPCC Assessment Report 6, Working Group 3, and it is now recognized in the Global Carbon Budget, the UNEP-GAP report, and even more importantly, it featured in the UNFCCC synthesis report for the global stocktake. So the document which serves as a basis for countries to work in the context of the global stocktake. So this document said, hey, look, when doing the comparison, be careful to compare apple and apple, not to mix apple and oranges. And the adjustment that we suggested was mentioned. Next. Yes, as a conclusion, essentially, the main reason for this big gap on LULUCF fluxes is relatively well understood. Is one of the reasons, the most important one. There are other reasons of differences. And the topic is how the anthropogenic forest sink is estimated. And this can be largely reconciled. However, other differences exist and a lot of work still to be done. From the countryside, there is need to increase transparency, completeness of estimates in terms of land uses and also carbon pools. And better, more transparent definition of area of managed land need to be put in country inventory report. Also more clarity of LULUCF in climate target. Global models could further improve the representation of land management processes and disaggregate the result in a way to ensure comparability, conceptual comparability with what country do. The next steps is to further increase comparability, make this comparison operational, and assess the implication. At the end, understanding and reconciling the LULUCF fluxes from countries and global model is key to assess collective progress in the Paris Agreement, and in general, to increase confidence on this very difficult and complex sector, which is LULUCF. At the end, confidence is important because if you don't measure or if you don't trust your measure, you don't manage. Thank you.
Yeah, thanks very much, Giacomo. And can I just say, I can still see some furrowed brows in the audience, but I have to say the communication of this has improved greatly over the last 3 years since we approved the land report. It really has come on quite a lot. What I would suggest we do, rather than stopping for any questions at this point, is that we continue to move through and go into a bit more technical detail. This isn't going to be an entirely Italian session, but we are going to move on to Sandro Federici, who is head of the technical support unit of the Task Force on National Greenhouse Gas Inventories for IPCC. He's a specialist in forestry, and before working for the TSU, he has worked for the European Commission, Italian government, the UNFCCC Secretariat, and the Food and Agriculture Association. You've got it all covered there, Sandro. So
Thank you. Too much. So my presentation is about how in the greenhouse gas inventories the land component is represented. So which is the approach, the basic approach implemented there to distinguish what is human emissions and what is not human emission. So the outline is the scope of the UNFCCC National Greenhouse Gas Inventories, identifying what is anthropogenic in the land, something about then the approach applied, how it, what it implies, how it has been implemented within the tiered approach of IPCC, and finally what are the actual fluxes that you have in the inventory. Okay, so the scope. A national greenhouse gas inventory is report emissions removal within the boundaries of the countries, but which are anthropogenic. Does not include whatever emissions removal from the territory of the country, only those that are anthropogenic. Now, for any other sector, it's easy. No? You stop at the human activity, you don't have an emission. But for the land sector, there are other drivers of emissions, natural drivers of emissions, that anyhow keep interacting continuously with the human activities. So the UNFCCC also decided that is the IPCC guidance that need to be applied. That's why it's so important that the IPCC approach, because it's the one that countries shall apply in their national greenhouse gas inventories. So, as I said, for any other sector, it's quite easy to distinguish what is anthropogenic and what is not. But for the land sector, in practice, what needs to be identified is the perturbation of the human activities on natural fluxes. From land, you have a continuous emissions of all the three main gases that are under consideration, CO2, CH4, and 2. And the human activities are perturbated these natural fluxes. Estimating carbon stock changes, as is the IPCC approach for land, is to look at 5 carbon pools and to estimate stock changes in the carbon pools. Why this? Because there is not a technology readily applicable and practicable, let's say, all across the world to measure in continuous the fluxes of CO2, no? You cannot do that. Then the fluxes anyhow is carbon, so you may measure the changes in the stock into the carbon pools, and you may derive from that the net emissions removals of CO2 that you expect have occurred because of the change of the carbon stocks. Estimating carbon stock changes anyhow means that you include the impact of the management of all disturbances. Let's just imagine a forest and the biomass of a forest, which is the easiest way to visualize all these. So you have a management, you harvest the forest, you plant trees in the forest. There are disturbances, wildfires, pests, whatever else. There are also other indirect effects. Management is a direct effect. I harvest the forest to get the wood. But the forest is subject also to other indirect effects. The most let's say, studied is the CO2 fertilization, the increasing in CO2 concentration in the atmosphere has a fertilization impact on the forest growth. Nitrogen deposition is another impact in terms of fertilization, so increment of the forest growth. The global warming itself is making forests in some areas in the boreal forest growing more because the growing season is longer than before. And any variation in the variables in terms of temperature and precipitation has an impact on the forest growth. So, because I cannot directly measure the impact of each of those, because I measure the forest, no, in the forest I have the biomass, I measure the trees, the stem of the trees, but the growing of these biomass there, or the decreasing because of harvest, fire, and so on, is the combination of the various drivers. It cannot be directly observed. There are models that work on the apportioning, but also there is no banal the issue, because all these elements, they concur together. So this is a very simple example, very banal. And this also to tell you that this aggregation of the effect is not just when you observe, because there are also consequences. There is a legacy of what happened for the future gain and loss, future emissions and removals from land. Here you have a managed forest land. Let's assume that's it, but no, this is a boreal forest. The boreal forest, the carbon stock that you have there is the consequence of natural variables, temperature, humidity, of the indirect effect, because we make the forest, we provide forest more CO2, more nitrogen, but also of the increasing length of the growing season because of climate change. Then I harvest. Is a direct human induced. Harvest is a real anthropogenic activity, but then I leave the forest naturally regenerated. This is what happened, for instance, in Italy, since this is an Italian forest session. But another occurrence could be a wildfire. Let's assume that is a boreal forest ban. It's something else, but I could not find the boreal forest. That may totally destroy the forest, but then the human activities reforest. I mean, in boreal countries, if a wildfire occurs, you don't leave the forest just regenerating. You actively replant the trees. So you see, all over this, you have the natural variables, precipitation, the pest, the insect, whatever else, interacting with your activities. So the conclusion was that there are all these direct and indirect human-induced drivers. There are natural drivers interacting continuously in the forest. And the conclusion is that the recommendation by IPCC is that you estimate of emissions and removals from managed lands as a proxy of anthropogenic emissions and removals. So what occurs in a managed land is taken as a proxy for anthropogenic emissions and removals. Of course, on unmanaged land, you also have this indirect effect. You have a CO2 fertilization, you have a nitrogen deposition, you have the change in the temperature and the precipitation regime also in the unmanaged forest. However, considering also the definition of IPCC, I don't know, this is a pointer? No. Well, see, no, it doesn't work, okay. You see, the definition of managed land of IPCC is quite coarse. So the vast majority of land are nowadays to be considered managed because they are subject to some degree of natural intervention. And the key rationale to conclude that the managed land proxy is to be applied is that the preponderance, as I said, of the anthropogenic effects occur on managed land. That most of the indirect effects also occur on managed land. That the so-called background in terms of emissions removal caused by the natural drivers in managed lands tends to average out across time. If you have a fires, the forest will regrow. So across time, the fires won't change your total carbon stock. Okay? So this leaves the anthropogenic effect in the managed land as the predominant component. And so estimating those, you estimate properly is expected that you estimate properly the impact of human activities. Now, however, the managed land proxy says that you need to estimate all emissions and removals of managed land, but this is very important, for which IPCC guidelines provide you methodological guidance. The IPCC guidelines do not include all sinks and sources occurring on land, even on managed land. Because those that are recognized, that have nothing to do with the human activities, and are not perturbed by human activities, are not there. Some example, CO2 fluxes on non-perennial carbon stock. If I have the grass have an annual cycle. They grow in a year and they're expected to decay in the same year, the biomass of the grass. So it's not there. Geological CO2 emissions are not there. Natural CH4 sink in mineral soils is not there. But also the natural N2O emissions from soils are not there. For those, there is only the perturbation. Countries are expected to report the perturbation in the natural N2O source only when you have a change in the total carbon stock of the land. So you change the land use, the total carbon stock of the land changes, then you have a perturbation and you estimate that one, and that's it. GHG emissions for permafrost thawing are not there. There is no a robust method for those. All emissions from non-livestock animals are not there. When you do a comparison in a city, for instance, between atmospheric measurements and the greenhouse gas inventory, you need to consider that the CO2 emissions due to not only pets but also to humans is a significant component of the budget. Otherwise, you will never close the budget. But other emissions are there. All carbon stock changes are there. You have the 5 carbon pools, biomass above and below, dead wood, litter, soil organic matter. You measure those. Changes in these stocks are in the inventory. All man-made sources of greenhouse gases are there. Agricultural activities. You remove the human beings, you don't have agriculture. So those are all anthropogenic, with no discussion. And also the perturbation, I was saying, the N2 emissions from soil mineralization is an example. The GHG fluxes from drainage and rewetting of organic soils. You just measure the perturbation there in practice as a change in time series of emissions across time in this case. And also the tiered approach does matter because IPCC has three tiers. Again, let's assume, let's look at forest, which is the easiest and also the most important of the land uses to consider. Applying tier 1, IPCC for dead wood and litter, assume that across time there is not a net change. So you may have annual net changes, but across time is assumed that it won't change. It's assumed that there is a long-term average. So these emissions are not in inventory. If you compare again with other estimates, you don't find there. You will find differences that are just because of methodological differences. But also at tier 2 and tier 3. It depends. If I use forest inventory data, which is the most accurate data that you may have for forest, because you don't measure the forest each year, you have a periodic stock change. So you don't know if in a year you have a big fire, those emissions in that year of the big fires are not in the inventory. Probably they will be spanned across the 5 years of the forest inventory cycle because of the impact anyhow the carbon stock. So a comparison year by year, finish, is extremely complicated, while across time can be better. I guess this is the closing slide. What actual GHG fluxes are included in the natural greenhouse gas inventories? I see it will be very useful that expert will produce a kind of diagram saying what is and what is not. This diagram may easily support the comparison effort between various communities. They may also guide further evolution of the models applied for IPCC, but working working group 1, working group 3, but also will help us to further evolve in the methodologies, and then may also clarify possible refinement of the managed land proxy. For instance, in the 2019 refinement, there has been a refinement of the managed land proxies with methods that allow to disaggregate one of the components, the natural disturbances component in terms of CO2 emissions and removals, may be disaggregated from the managed land proxy. This may help, may enhance the comparison with other methods. Sorry.
Oh, okay, thank you, Sandro. And just say, before we move on to the next speakers, we've got about 10 minutes each, so if we could move it on a bit. But just one final observation on your last point, Sandro. It does seem to me that the current definition of managed land leads quite a lot of flexibility for interpretation, which means that if you make a liberal interpretation, yes, you may capture quite a lot of natural fluxes.
We consider that as a first order approximation. Yeah. The refinement is a second order approximation for a component of that.
Yeah. Okay, thanks. So let's move on. We're now going to move on to bookkeeping models. And the only member of the panel I haven't met before is Julia Pongratz, who's a professor at the University of Munich. And she has been a contributing author for IPCC Working Group 1. But the key thing for this is that she's on the Scientific Steering Committee for the Global Carbon Project, which coordinates the estimation of land use emissions that's used as the baseline for the IPCC emission scenarios. And I think that's the key thing. Julia, over to you.
Yeah, thanks very much. So there's various model approaches how you can simulate land use emissions. Elena is going to speak about DGVMs, vegetation models. Later, I'm just taking the part of the bookkeeping models. But I do acknowledge there's several parts, and we all run them in my group as well. But bookkeeping now. So what's that exactly? So here's a very simple sketch of what a typical bookkeeping model looks like. So you've got 3 parts that you need to combine. The first is you need to know what the carbon densities are of the different ecosystems that can undergo land use change. So here on the top you've got a table, so you can use that from literature-based estimates. You could use the FAO carbon stocks to derive carbon densities for the different countries. You can use maps based on observations or models to create these carbon densities. But that's the one thing that you have for all vegetation types, including also agriculture on different ecosystem or in different climate zones, cropland and pasture, you would have values there. Then you need to know what vegetation exists by the time you start your simulation. So usually you use potential vegetation in the absence of human interference, and then any subsequent land use change can tell you what has been transformed to your new land use. And when you abandon agricultural land, you would also know what it can return to naturally. And then, of course, you need to know the land use dynamics themselves. So the land use transitions and between all the different types, pasture, croplands, between forests, non-forests, and so on. There's various data sets that you can use for that. The one that's most commonly used, and that's also being used mostly by the dynamic global vegetation models, is LUH2, the land use harmonization product that we created for the CMIP simulation, so the climate model simulation that underlie the IPCC projections. Good, so you have these 3 things, and now you know your dislocated carbon, right? Because you know how land use areas change, and you know what the carbon before and after the land use transition should be. But you know you're missing 2 informations. The one is, where does the carbon go? So if you clear a forest and there's cropland afterwards, you've got a difference in carbon stock, you need to put that somewhere. So you've got different pools, different product pools, for example, paper or construction wood and so on. You also have slash that's left on site, so you've got a litter pool, you've got soil carbon, vegetation carbon, and so on. But also, of course, it's not equilibrium, a forest and a crop all in equilibrium, but you need a transition. So you need to know response curves. So when a forest is cleared, The wood products decay slow over time. The fire, if you use fire to burn, that would go up in the air very quickly. And also the regrowth of forest would take a while. And so you've got these dynamics built in based on empirical data into those bookkeeping models. And then voila, you've got your net land use change flux. It's called net because there's a whole lot of different processes in there. So you've got clearing of natural vegetation that typically releases emissions, but not always. You've got abandonment of agricultural land that very often leads to removal of CO2 from the atmosphere. We've got transitions between different types of agricultural land, crop to pasture or the other way around. We've got wood harvesting, including product usage. So wood harvesting is very interesting because on the one side it's emissions to the atmosphere from the products decaying eventually, but it's also an uptake because forests can regrow. Currently it's a source globally to the atmosphere, but we could change that. What's also partly considered by the bookkeeping models is afforestation. So reforestation is always covered, right? But afforestation on a place where there has not been a forest in the past, which the potential vegetation maps don't know about, therefore, that's not necessarily captured by all models to the full extent. So if you afforest the deserts, the Sahara, you couldn't capture that with these models. Degradation of forest is partly captured, but not to the full extent. Current studies show degradation could be a major player in Brazil, for example. So with that I mean that the forest remains a forest, but there's edge effects, there's hunters going in, there's mining effects on it. Fire suppression, which would mean that the forests are denser than they would be naturally, is also not captured by all those models in the same way. What the models don't capture is peat drainage and burning, thus emissions from organic soils. That's not needed because we've got good external data sets that we can use instead to add those to the net land use change emission estimates from the bookkeeping models. So, what are the uncertainties? I was asked to speak about the uncertainties, and they are big. So in the global carbon budget, the land use emissions are the term with the largest uncertainty. The reason is there's no Earth observations on land use change emissions. Because when you observe the planet, you see everything combined anthropogenic plus natural dynamics. So a forest may be gone because we cleared it for agricultural purposes, but the forest may also be gone because a natural wildfire occurred or drought. But that would be part of the natural land sink. It would not be part of the land use change emissions. And therefore, we need models. Only models are able to isolate cleanly the effects only from land use change. And that's part of the reason why there's substantial uncertainties. But we try to get behind that. There's a range of studies that I'm citing here that show you what are the major factors for why model estimates of land use emissions across bookkeeping estimates differ. One is the land use forcing. I mentioned LUH2, there's other data sets around, and you do see that they show quite a big difference. It's really hard to observe land cover change induced by land use from space. The comprehensiveness of land use practices is also something that's very differently assessed. In particular, shifting cultivation is hard to assess, and when you switch those off in your model, you would find that your land use change emissions become substantially smaller. That's also one of the key points that we need to evaluate against the national greenhouse gas inventories better, because there too the shifting cultivation is assessed very differently, maybe even less comprehensively than in our models. Model parameterization is a big issue too. So I showed you that there's a whole lot of data going into these models, and what data you use there for the carbon densities, for the allocation to product pools, for the response curves. You have to make choices what data you use, and you could also make other choices. So in this figure I showed you here, what we did was we used blue. Blue is the bookkeeping of land use emission model, so the bookkeeping model we developed in my group. And we then exchanged different parameterizations by those from the Houghton and Nasika's model, another bookkeeping model. And step by step, you could then identify which are the major factors for uncertainties in that way. The standard blue estimates are here in dark blue. They're rather high. Why are they so high compared to the standard Houghton and Nasika's model, which you see in black? Well, for example, when you look at the light blue curve, you see when we exclude subgrid scale transitions, when we switch off that shifting cultivation exists in the reality, in the model, then we would get quite a bit lower emission estimates. if we use the carbon densities that Ski Houghton uses in his model, then we would get, again, much lower. That's this thin, dark red line. So the choice of carbon densities makes a really big difference in terms of the emission estimates. So, yesterday in the Global Carbon Project, we released the annual Global Carbon Budget 2022. I'm sure you were all up 1 minute past midnight to see that happen. So these are the latest estimates. You see what I mentioned before, a big range, a big uncertainty around land use emissions. We do see a slight downward trend over the last 2 decades. I would not say this is robust yet. We need much more ambition on stopping deforestation to make that so strong that we see a downward trend that's statistically significant given the large uncertainties around it. So the land use emissions have been relatively stable, I would say, over the last 50 years, and too high, if I may add that. So this uncertainty estimate is stemming from global vegetation models, expert-based judgment, and the middle line is the average of 3 bookkeeping models. I mentioned the blue model, there's also the Houghton and Asikas model in an update, and the OSCAR model. So these 3 models all provide bookkeeping estimates. Down there you see the spread-in models, again, for the latest budget estimates. So you do see these quite different estimates and also dynamics. Oh, sorry. And these estimates, we don't just put them out for fun in the Global Carbon Project, but they are subsequently used, and we're happy about that, of course. So they're used in the IPCC assessment reports, also in AR5, but in the 6th assessment report, they're used in Working Group 1 and Working Group 3. When I speak about IPCC, just a short note here, I mean something different than when Sandro speaks about IPCC. So you're referring to the IPCC guidelines on how to do inventories for land use change. I'm speaking out at the IPCC assessment reports here, where the best data is put in an assessment. And this data is also used in the UNEP GAP report that came out 2 weeks ago, and so on. And a last note, because how does this all relate to this session? This figure, the core part, you've seen from Giacomo before. And in the Global Carbon Budget, since last year, we do operationally this mapping from the bookkeeping models to the national greenhouse gas inventories. So what we estimate with the bookkeeping models is the red bar. As I said, only those fluxes that are really driven by land use dynamics, nothing else. That's how we define it with the global vegetation models. But then we've got natural fluxes like CO2 fertilization occurring on forests. That's, we would call, a natural part of the natural land sink in the Global Carbon Budget, and therefore we assess that with dynamic global vegetation models that Elena speaks about later. That would be the green bar. That's the natural sink on managed land. And you see with the gray bar, that's taken together is what the national greenhouse gas inventories quantify. Up in the text you see how our numbers compare. When we estimate in the Global Carbon Budget that the natural fluxes on managed land amount to minus 6.6 gigatons CO2 per year average over the last decade, the land use emissions over the last decade are 4.5 billion tons of CO2. And when we add those 2 together, you obviously get a sink of 2.1 gigatons of CO2 per year. And this is very close to what the national greenhouse gas inventories quantify, which is 2 gigatons CO2 removed each year. So there's a big difference again, as we see. So we have 4.5 gigatons emissions to the atmosphere in the Global Carbon Budget. The greenhouse gas inventories tell us there's a big sink there, but it all makes sense because you can translate one to the other. And we're quite excited that the numbers are so close together, because this means that our operational estimate that we put out each year on country level, even going into component fluxes like deforestation, forest fluxes, and so on. So this really provides a way forward to an independent evaluation, both of the models and the country data, and also really then shows us if we're on track on meeting our targets under the Paris Agreement. Thanks.
Oh, okay. Thank you very much, Julia. And we love the optimistic messages that scientists can actually agree and get to a similar answer. We're now going to turn to the next sort of jigsaw piece in the puzzle, and start to look at the global dynamic vegetation models. I'm going to hear from Elena Shevliakova, who works at NOAA, and she was a coordinating lead author on the special report on climate change and land. So over to you, Elena. And nice to see you, because the last time I saw you was at the land approval. Yeah.
Hello? Hello? Hi, thank you for giving me this opportunity to describe what I do as a land modeler. I actually work with climate models. And let me just explain to you what is inside this machinery. Is this? Oops. Yeah. So what is a dynamic global vegetation model? It's a set of mathematical equations which represent biogeochemical cycling of elements such as carbon, not just in vegetation, but also in soils, because those are two major reservoirs for carbon and other elements inland. And they simulate that dynamics or cycling both on managed lands and on unmanaged lands. And those cycling responds to climate change and climate variability, to changes in atmospheric composition of CO2 and fluxes to land, such as nitrogen deposition, but also to land use, land cover changes, which are usually represented via combinations of the model parameterization for anthropogenic activities and scenarios. And scenarios, we're going to hear more about them from Kate. So, major difference with bookkeeping approach, that nothing is described in terms of vegetation or soil carbon density. It's all a product of the model. It's fully simulated. And those simulations are typically computed on a grid. It means the Earth is broken into little boxes. And in each box, you know what the climate is, you know what land use scenario is, and you know what the vegetation, the soils are doing. And because it's a big model, you carry those simulations from often like pre-industrial into 2100. You need a big computer to do it. And you could do it standalone, meaning you give it a climate observations, or you could actually plug it into Earth system model. That's what Working Group 1 does. Oops. Oops. Sorry, I did something. Okay, if one looks under the hood of these DGVMs, you would see a combination of different submodels. It's actually dozens of them. Some of them represent natural processes such as photosynthesis or soil respiration, and others represent processes which are due to human activities. For example, you could look at the clearing of the forest, or you could look at the harvesting, and you could abandon the forest and see how it regrows. There are different kinds of uncertainty in these models. One we call parametric uncertainty, because even if everybody uses photosynthesis model, parameters of those models would be different. But also if you compare one DGVM to another one, they might not have necessarily the same processes, particularly for the land use. And there is one big uncertainty which often we forget, and it might play actually a role in this reconciliation, is what are the responses of soil to wetting and warming? Because those respiration fluxes from soil happen both on managed and unmanaged land. Another big issue is how do you project future vegetation distributions? A lot of models still prescribe them. In IPCC, among ESMs, there are only 4 models which actually had vegetation dynamics models. So it would be some uncertainty due to what is those forests are going to be and what they're going to look like. Next. Okay, how do we represent land use on managed land? If you zoom in and look at each grid cell has a description in terms of composition of different land use types or fractions inside that one grid. And it also tells us how those partitioning change in time. We give it a scenario, which some model use gross transitions, other use net transitions. And then you take this part of land which you think been, for example, cleared from primary or unmanaged land and ship it into the cropland when this become a cropland. When you send that parcel of land to another land use type, what you do, you carry all the carbon it had in soil, but also you do something about the fluxes, like cleared fluxes. You make assumptions about where that cleared flux goes. And I think the inventories and land models often have very different assumptions about where does it go. Up in the air, what goes into soil, what happened to residue. So there is also like combination of these uncertainties about regional specificity in the land use activities and the fate of that carbon, but also how many different land use types each model can include. one of the limitations of DGVMs that many DGVMs still do not represent wood harvesting and they don't represent secondary vegetation as separate land use type. Another problem with DGVMs that even if they do a lot of these transitions, they cannot report fluxes on soils because often in DGVMs you could have different pools, fractions of those vegetation for croplands, for pastures, but the soils among them is all one big pool. Because of that, you cannot actually say in the model where that respiration comes from. So it's one big soil flux per grid cell. And because they simulate those fluxes, the net carbon balance is correct. But because they cannot report that by land use type, so what they often do, they come up with approximations. So how do the GGVMs, most of GGVMs, approximate the land use flux? They make assumptions about different climate change and different land use change, and they combine those assumptions and then look at the differences between the fluxes. A very typical way of doing the net land use flux on managed land to carry two simulations, so-called S3 and S2. That's been used pretty much in all the assessments before and in the Global Carbon Project. S3 is a simulation where you include everything. Land use scenarios, climate change, atmospheric CO2 effects, so-called CO2 fertilization. And then you do another simulation, which is S2. You say, okay, my climate is going to change, my CO2 is going to change, but I'm not going to change my land use since 1700. So you look at what carbon flux would be on land if you don't do any land carbon change. You could still have some pastures and crops back from 1850, for example, but you don't have anything new which happened in the world. And the difference between those fluxes, this is a red curve in the second panel, would be like approximation of this net land use flux. It's not the flux which happened actually, which is the flux which didn't happen. It's so-called lost sink capacity. And if you compare that to the land use flux in the simulations, for example, where you only change land use, which is S4, and don't change the climate, that flux is actually much smaller, so you have a smaller source. And this is example from the model which Julia did. It's from J.S. Bach as a German DGVM, and you could see that if you use the pre-industrial climate and only land use, your source, your land use flux, is going to be about 0.5 gigaton. This is carbon, it's not CO2, by the way, would be smaller. So the whole approach, by differencing, actually overestimate land use fluxes because it includes fluxes which didn't happen. So, but some models do represent land use fluxes by land managed proxy. So what if we look at few of them and see, is it consistent with this picture? What do we learn from them? So we have a model like that. We develop in my lab at NOAA-GFDL, but there are other models which also could do it. There is one in Australia. There is also some models we develop in Europe which look at soils separately after land use, and then they compute net fluxes on those land as a result. So if you use managed land proxy approach and you look at what's happening on those models, you could try to understand, is the differences approach is the same as land managed proxy approach. So the black curve is before. It's a differencing or opportunity flux which didn't happen. It's again the bigger source. The green line is from the pre-industrial simulation with only land use changes. You could see similarly, sorry, the red line. That red line again produces a smaller source than before, similarly what J.S. Bach did. And the green line, it's a carbon flux only on managed land. You see, surprisingly, the pre-industrial approach and the land managed proxy approach produces similar carbon flux, which is a good news. But that flux started to diverge in 1990. I think we didn't completely figure out that. It's probably because climate change is accelerating. There is something happening there which has effect of climate change. We also made some assumptions about croplands in this simulation, and they're actually important. So what do you assume particularly about deforestation when the land converted to croplands? And it also matters, like, what do you actually assume about lifetime of the carbon emissions after land been deforested? So I could go look inside that my green curve and now look by land use category and see what is actually land doing. As you can see that, the blue line is secondary lands. Cyan line is a natural flux. Green and red is the pasture and rangelands. And the black one, which is the source, is the croplands. Croplands also include deforestation due to conversions of the land to croplands. I also want to note, when we say deforestation, in DGVMs, it's not just deforestation, it's devegetation, because land model doesn't care. It's a forest, it's a shrub, or it's a woodland. It basically cut all the vegetation and sends it somewhere. So amount of carbon which we send into DVMs in this deforestation or cleared fluxes, I think is bound to be higher than what you would do if you would do inventory, because some stuff just, even the grass biomass would be shipped there. And as we send that soil carbon, it sits, you know, the soil carbon which was in the forest, it will come with your deforestation fraction into cropland and will sit there and emit that carbon. Both because, temperatures are changing, wetting is changing. So those inherited fluxes from the forest or from other vegetation lands going to contribute emissions on your cropland in DGVMs. So also there is another interesting point about what area to look. Because when we get the scenario from CMIP 6, the scenario start counting secondary lands from 850. It's not a typo. That scenario is not from 1850, it's from 850. So the area of the secondary lands in our simulations could be much bigger than what would be in inventory. But we could actually look by age. You see on the right is a plot about the emissions on secondary lands, and the dashed one, if I only look at the 50-year-old secondary lands, is still a big source. But it's still smaller than if I would just look into like entire 1850 simulation. So I think what we found surprising that a lot of the sources we see in our net fluxes actually come from amounts of deforested towards cropland and actually from the soil respiration which is associated with those croplands. We also make different assumptions about where they get this cleared carbon. So we just dump it in this model on the soil, but I don't think it's what the assumptions which made into inventories. So anyway, but I think using a few models we have and looking inside of the managed flux and understanding what are the secondary lands are doing and what are the croplands doing, particularly soils, could be a pathway to reconcile the inventory in lands, because those two pretty much drive the net land use flux. But because the way we create our simulations is so different, the way we count our lands are different, and what soil carbon we include, not just 30 centimeters on top, but entire soil carbon column, could explain some of these extra emissions which we get in the DGVMs. So key messages. I don't think it's informative to get just global net flux from DGVM and look at the global flux which inventories provide. You really need to understand the pieces. You really need to understand components. You need to understand what vegetation is doing, what the soil is doing, and what are the areas. It's not just forest. It's actually all the lands which need to be either included or they have to be excluded, so it's the same areas of the world in the part of this analysis. I think we also need to understand assumptions in DGVMs about fate of cleared carbon, because that's one of the major sources of uncertainty and also a difference with what the inventories would do. And the modeling community need to characterize structural uncertainties in DGVMs to compare overall land use model representation. If somebody doesn't do wood harvesting, there's no way they could get correctly the fluxes. So, but I think, fundamentally, I think we really need to talk to each other. And I think we could reconcile them, but we have to start small and look at components, at pieces, and the different carbon stocks. That's all.
Okay, thanks very much. Thanks very much, Elena. Okay, we've got two more presentations, and if people are fairly crisp, we will get time for questions. So the next speaker is Kate Calvin, who is currently Chief Scientist at NASA, which I think is completely awesome. And Kate is also hyperactive in IPCC. She was a coordinating lead author on the land report. She's a lead author in Working Group 3, and she's playing a key role in the synthesis report at the moment. So I'm glad you found time to come and speak to us, Kate.
Yeah, thank you, Jim. So I'm going to talk about, Julia and Elena talked a little bit about how we model the past. I'm going to talk a little bit about how we model the future and how this relates to this topic. And so specifically, I'm going to talk about integrated assessment models. And I'll just say as I'm going through here, Oh, went too many. Let's try that one more time. So each integrated assessment model is slightly different. I'm going to talk what's generally what's true, but there are some model-specific differences that I will try to highlight. Okay, so first what I want to do is talk a little bit about the approach to anthropogenic and natural emissions in an integrated assessment model. So first, how do we define anthropogenic? So in an integrated assessment model, the definition of anthropogenic emissions when it comes to land use and terrestrial carbon dioxide is land use and land cover change carbon dioxide emissions. So this is very much related to what Julia called the net land use change flux. So it's a very, very similar definition. This is calculated directly in the integrated assessment model, and for many of the integrated assessment models, they use a methodology and an approach that looks very much like what Julia showed, sometimes using the exact parameters and functional forms that were used in the bookkeeping model. So it's very comparable to what is done there when it comes to anthropogenic. So part of what we use, and I'll come to this later, that we use an integrated assessment model for is to understand what future climate might look like. And in order to do that, we have to actually represent all of the emissions that contribute to warming. So we do also consider natural emissions, but this is handled a bit differently with a different definition, as Giacomo pointed out, than you might see in the inventories. So for an integrated assessment model, the definition of natural emissions is the response of land use to human-induced environmental change. So changes in temperature, precipitation, carbon dioxide would all be captured as part of natural emissions, regardless of which land type they're on. And typically, in an integrated assessment model, this is actually calculated with a different component of the model. So integrated assessment models will have representations of land, of energy, of water, and they'll also have a representation of climate. And that's often done with a climate emulator, and some of those are commonly used across integrated assessment models. We can also use a full Earth system model or a DGVM, like Elena talked about in that, to do that calculation. I also just want to mention one other thing here that Giacomo mentioned the word managed and unmanaged before. And it's not here, but if you do see the word managed when it comes to integrated assessment models, it's not always the same way it's defined as in an inventory. So for many integrated assessment models, managed land has to do with what you're doing with the land. Are you logging on it? Are you producing a wood product that is sold into a market? That would largely be categorized as managed. They would categorize something that is freestanding and not used there as unmanaged, where in an inventory you might define those differently. So just wanted to highlight that. So the next thing I want to talk about is why that we do this. So what is the rationale for the decisions made in an integrated assessment model? And really to do that, I want to talk about what we use these models for. So one of the reasons that you use an integrated assessment model is to understand the implications of a long-term climate objective. So if you're thinking about what does it look like to limit warming to a particular level, you might use an integrated assessment model to calculate the emissions, the energy, the land use change consistent with that warming level. And so that means that we capture all aspects of emissions in those models in some way or shape or form. The second reason you might use an integrated assessment model is to understand interactions between systems. So how are energy, land, water, and climate related? And for many of the integrated assessment models, they started in the energy community, and so they were focused really on energy transitions. And land came about because you wanted to understand how does the way you produce energy affect the land. So if you're using bioenergy, you might need land for that. And so trying to capture those interactions is one of the goals of these models. Another reason you might use an integrated assessment model is to quantify the implications of a specific response option on land emissions or climate. So what if you want reforestation? What does that look like in terms of land or emissions or climate? What if you're thinking about a different energy technology? What does that mean? And so again, capturing these interactions among sectors and understanding what-if scenarios for the future. The last reason, and this really gets to part of why we've divided anthropogenic and natural differently, is one of the roles of an integrated assessment model is to provide inputs into Earth system models, which then calculate changes in carbon, climate, and Earth system. So if you look at the IPCC Working Group 1 assessment report, they focus on 5 illustrative scenarios. Those scenarios originally came from the integrated assessment modeling community. So integrated assessment models produce future trajectories of emissions and land use and land cover, and then gave that information to Earth system models who could then look at the physical climate system and the biogeochemical changes induced from that. And so for that reason, we want to be very careful about how we define things and what we pass from one model to the next to make sure we capture all of the changes in the Earth system, but only capture it once throughout the modeling chain. One of the questions I was asked about was on uncertainties, and I'm not going to show you actually a slide of uncertainties completely. There is a little bit of it here, but I do want to just highlight one of the primary uncertainties you'll see in an integrated assessment model is actually the future scenario. So how, what happens in the future in terms of energy, water, land, and emissions is one of the primary uncertainties, and that will play out in the land use change carbon dioxide emissions that you see in those results. Some of the other uncertainties are some of the ones that Julia mentioned. As I mentioned, we use a lot of similar approaches to the bookkeeping model, so the uncertainties that affect bookkeeping models would also affect an integrated assessment model. So for this slide, I just want to do one more thing on how we use these, and this is a figure from the recent IPCC Working Group 3 report, which is showing you different ways of limiting warming to 1.5 degrees. And so it's showing you the sectoral emissions associated with it. The first bar that you see on the left is historical. The next 5 are 5 different future scenarios. And this is just to highlight that point that the role of land and land use and land cover change does vary by scenarios. But this is the type of information that you would get from an integrated assessment model and how you might use it in an IPCC report. Just to conclude before I hand it over to Detlef for the final presentation, just to directly link to some of the things you've heard before. So with respect to inventories, in some cases, inventories can actually be used as a direct input into integrated assessment models. That's not typically true of land use carbon dioxide, but for other gases, you might actually use that as an input so you have a common starting point. What I would say is more common with the terrestrial carbon dioxide emissions is to use an inventory as a benchmark to evaluate your model against. So you construct your model, you run it through the historical period, and then you can compare and see how it's different. So that's one way we relate to inventories. For models, I've already mentioned that we use a lot of the same approaches as the bookkeeping models. We also provide inputs into the types of models that Elena mentioned. And now I'll just hand it over to Detlef for the final presentation.
Thank you, Kate. Can you hear me?
Okay, thanks. And we're, as I say, finally, we're going to be joined by Detlef van Vuren online. Detlef is a senior researcher at PBL in the Netherlands. He's also a professor at Utrecht University, and he's a member of the board of the Integrated Assessment Modelling Consortium. And as I understand it, Detlef, you are going to take on the huge challenge of tying all these different threads together in this final presentation.
Yeah, that's correct. Can you hear me, Jim?
Yes. Yeah, we can hear you.
Okay, perfect. And you can see my slides as well.
And we see the slides.
Okay, great. So this slide has been shown in earlier presentations, among others by Giacomo. And it explains how bookkeeping models, and as Kate indicated, or the IEMs, and as a result of that also the Working Group 1 models, because they use the scenarios from the IEMs, look at the emissions from land use change. And so the emissions from land use change itself and from forestry, so clear anthropogenic activities, are recorded as anthropogenic, while the uptake of CO2 by forest is all regarded as natural. And as Giacomo indicated, and also was part of the second presentation, the country inventories have a slightly different definition. And so they agree that the land use change and the intensive use of land are anthropogenic, but they also take the uptake of CO2 on managed forest as being anthropogenic, and therefore have a slightly larger definition of anthropogenic, and they have a slightly different definition as well of the natural sink. And so something that is important now is that all the IPCC data from Working Group 1 on carbon budgets, but also all the outcomes of Working Group 3, which are based on the IEMs, are consistent with the way that the bookkeeping models and the IEMs look at the world. So we have two ways of reporting land use change emissions or land-related emissions, and both are valid, but they are different. And it is important to know that this is different from the normal uncertainties that we have anyway in land use related emissions, as for instance was part of Julia's presentation. So we have quite some uncertainty in those emissions, but unrelated to that, we simply also have difference due to these two different accounting methods. Now, as I indicated, both methods are in principle okay, but if consistently used. But if you start to mix them, then obviously it becomes a problem. And I would like to explain that a little bit further. And I'm using these two icons for the country inventories and the global models as an indication of these two methods. So first of all, starting with the bookkeeping models. So we have the energy and industry emissions. We also have the emissions from land use change, which is, as I explained before, the real land use change emissions and some of the forestry activities. And then on the bottom side, we have these natural carbon flows, the carbon flows into the ocean, but also the carbon flows into managed forest and natural forest. And so these are considered to be natural carbon fluxes. This is in contrast then to the way that the country inventories see the world. And both look at exactly the same world, so there's no difference in the content, but that single flow that is on the left side part of the natural fluxes is on the right side part of the anthropogenic fluxes. And as a result, the anthropogenic emissions on net are slightly lower, because it's a negative flux. And at the same time, it also means that the natural uptake is also somewhat smaller. It's simply a reordering of the emission flows. So we can easily understand why there is this couple of gigatons difference between these two methods, and we can recalculate it. But can we also do this for the scenarios? And luckily we can, because we know the maps of the scenario models. We know to some degree what grid cells would be regarded as managed forest by these models, and we could follow the budgets of these relevant cells in geographically explicit IAMs or DGVMs, and then calculate the carbon uptake. It's not 100% precise, but it will do for the moment. And so what you would get is shown here. So on the left, we have again the way that in principle the IPCC reporting sees the world in Working Group 1 and Working Group 3. And then on the right, we have the country's approach, and then we could include there also for the future the corrected uptake by managed forest also on the right. So it simply takes that flux from the left bottom graph and put it into the top right graph. And you have slightly lower emissions. And you can then also calculate the carbon budgets that are associated with this. So on the left, you would have the direct reported carbon budget by IPCC Working Group 1. So for instance, in this case, 930 gigatons of CO2 for a 2-degree type of scenario and a net zero year around 2070. But you then can also calculate for the exact same scenario, simply correct it to be consistent with the country inventories, and you would find that in that scenario, the anthropogenic emissions can only be 760 gigatons under the definition used by UNFCCC, and the net zero year would be somewhat similar by the IPCC reported numbers, only a little bit earlier. And so the important point is both methods are talking about exactly the same world, but we have simply under different accounting rules, so different numbers. And the difference is quite a bit. So under the accounting rules of UNFCCC, your carbon budget is only 760 gigatons. Yeah, if you would make the mistake to take directly the IPCC numbers and also combine them with the numbers from the UNFCCC, then things goes wrong. Because then in that case you would emit way too much, and you would in the end lead to a higher temperature outcome. So you have to make this correction. And the nice thing about the correction that we have done, and it's published in a paper also led by Giacomo Gurasi in 2021, is that you can actually do that also for all regions, because you're doing it on a grid cell level. And so here it's shown that in principle for most regions it does mean that the IAM original output can be reconciled with the UNFCCC inventory data. We can also do it for all scenarios. So in that paper that I was talking about before, we actually did it for all the SSPs, all the scenarios that are used by working group 1. And you can see that it does lead, it works for all the scenarios, but it does lead to quite some changes in the carbon budget. And so the carbon budget for the for a 1.5 type of scenario, 1.5 degrees type of scenario, the SSP2 1.9, the carbon budget would be adjusted by 100 gigatons of CO2. For a 2-degree type of scenario, it's adjusted by almost 200 gigatons of CO2, and for higher levels it would even be larger. But at the same time, interestingly, the impact on the net zero year is much smaller, and we can actually understand that, because the difference is caused by the carbon uptake from managed forest. The moment that the emissions approach net zero, actually that carbon uptake is going down, and as a result, also the difference between the two approaches starts to disappear. And so the rules of thumb are more or less the net zero year becomes slightly earlier, and there's a big impact on the carbon budget. And so to summarize it, if a policymaker using the UNFCCC inventory method is asking to IPCC what is the remaining carbon budget for neutrality under 2 degrees scenario, then the original answer by IPCC would in this case be 930 gigatons of CO2, which is consistent with the bookkeeping method that has been used in the IPCC calculations. But the problem now is that it's not comparable with the country data, and so it needs to be adjusted. And we can make that adjustment. We can at least make a reasonable estimate how to do this. And in this case, we would then have to say, you have to recalculate it, and your remaining carbon budget would be around 760 gigatons of CO2. And your net zero year is, might be a little bit earlier. And, okay, sorry about this. So this means that we have a method to do this, and it also means that the carbon budget, if you combine it with the UNFCCC approach, is somewhat smaller. Luckily enough, the impact, as we know, on the net zero year is not as large, which many countries are focusing on the net zero year, so that's a good thing. So this is how I wanted to reconcile what we have seen so far. So it's an important issue, but we can correct for it. Thank you.
Okay, thank you very much, Detlef. This has been quite an ambitious panel, and there's been a lot of technical depth in it. So I will just say we've got a few minutes left in which we can take questions either from the floor, or we've also got the possibility of questions online. So floor is open over there in the audience.
Hello everyone, congrats for the presentations, and my name is Marco Romero from Angola. I would like to know from your different perspectives, what is really the mismatch or the bias between ground data and remote data that is getting together to map these emissions, if that's the case. And the second question, if you don't mind, is on the ground to help having all those index, how really people can be educated on how going to all those emission mappings without having those bias or errors at a national level. If that's the case, if we can narrow down the resolution to a national level.
Okay.
Yes, I could start. Just to clarify, your question was on ground data and remote sensing data. Okay. Yes, yes. Of course, we did not specifically address remote sensing. Of course, remote sensing data is part of the input of some of the models we have listened, and to some extent also for the inventory. Of course, there is there is a booming of new remote sensing data that can potentially be very helpful to provide input data to inventories or to provide independent verification to that. I would then maybe ask Sandro to complement and further.
Greenhouse gas inventories data shall be unbiased. This is the assumption. So, of course, then if the country need to do all the effort to produce unbiased data. But remote sensing is not biased too. The problem of reconciliation is, as I shown, the inventories are a subset of all the emissions removals that occur. The satellite may see much more. So it's very important to disaggregate what the satellites see in order to compare the two. Okay?
Okay, any more questions from the floor? Yes, please, a second row over there.
Thanks. So thank you very much for very inspiring, exciting, and so very nice presentation. So I'm Tomo Aizawa from UNSCC Secretariat. So I'm dealing the inventory stuff, so and also the review stuff. I have 3 questions. So I would like to start from the simpler and the easier closed question. The first one is for the urea. So I saw some spike in the middle of the 90s. So all the models have some small spike, not small spike between 16 and. So I'd like to know what is that. And the second question is maybe for the Giacomo and Sandro. So in the inventory, as we know, so the carbon stock changes. If it is lost, we assume it is will be emitted sometime. But actually, it is not emitted. So staying in the carbon like here. But the carbon gain will be accounted as a removal. So that is okay. So then I think this is marginal differences. I'm curious about this difference may affect the differences between models and the inventories. So this is the second question. And the third question is for all the modelers, the Julia, Elena, Kate, and Detlef. So I'd like to know, how do you verify the result of the model? So also I'm interested in to compare with your result can explain the past trend of the concentration in the atmosphere or not. Because I believe inventory monitoring, even satellite or Zonde or Flux Tower or something, and inventory monitoring and also the modeling, these 3 should be consistent or something. So otherwise we cannot verify the data, and also the policy actions cannot define how they should do. So I'd like to know these things. So then how do you verify your result of the models? I'm interested. Thank you very much.
Good. I start. That's a quick answer. So the spike you saw was in 1997 in all bookkeeping models. This is peat burning in Indonesia. It was an El Nino year, extremely dry, and there was a chance taken to clear a large vast of this peatland forest. I can quickly answer to the verification part for the bookkeeping models. So we do integrate new remote sensing data into bookkeeping models, like biomass estimates, time series over the years. So that's one way to make them even closer to Earth observations. How do we evaluate or verify them in the end is partly together with the land sink term, because then you can use inversions, and with the inversion data you can pin down where exactly your net CO2 flux on land stems from. We can take out the fossil one because we know the sources very well, and so with inverse modeling we've got some independent evaluation, and this is something we already do related to the Global Carbon Project.
Okay, if I got your question was about the harvested product, the carbon included. So at global level, we do have estimates of that based on country reporting. It's not a huge amount, it's not negligible, but we are speaking about a 0.3 gigaton, 300 million of tons of CO2, which is not a small amount, but is around, say, 5% of what country themselves report as a net sink from forest. So when we compare these, the country inventories with models, we try to keep consistency. For example, IAMS, correct me if I'm wrong, but in that paper we removed this value from inventories because IAM do not have these, not all. While bookkeeping models do have that, so we included these, trying to compare apple to apple as much as possible. So it is a small, not negligible component, but not so huge. Doesn't explain much of the difference.
Yeah, the inventories, it depends if the harvestable product is a pool for which estimation are provided. If it's not, of course, the comparison is big because all the harvest is assumed emitted in the year which occur, which is a large quantity usually. But as Giacomo said, if you include the harvestable product, the annual change is small. So having it make the difference are small, even if you have different system of accounting. But not having the harvestable product pool counted, the differences are large.
Hello? Yeah. When you develop a land model or dynamic global vegetation model, you start by evaluating fluxes and pools. And we use remote sensing data, for example, to look at above ground biomass, which model simulates on the land's distribution, not just the totals. So that's probably the best data we get from remote sensing to look at the global distribution. We also evaluate wood harvests, because when we get the scenarios from reconstructions, it comes with the numbers of wood harvest, which is used to create that scenario, which tells us what the wood harvests are, for example, in time, and by region or by country or by grid cell, actually. So, and we compare what we assume being wood harvest in our model, because we do have wood harvesting. So the things which we cannot evaluate often, it's a cleared, like a deforested carbon pools. We look for numbers like in bookkeeping models and see what do they report. But those pools, those fluxes are the hardest to do, among the hardest to do. And the one which is the hardest almost to do is soil, because there's no remote sensing. Inventories for soils, I think, far less detailed than for the forest or vegetation. So we often look at maps, but the maps often report only 30 centimeters on top globally. There are some deeper ones, but the models simulate everything under the ground. So in some sense, one of the largest uncertainties in the models in terms of stock is actually what do soils do. So you look at sometimes individual sites, like if the fluxes or the pools are simulated. But I think in terms of reducing this gap, if we get some sort of comparisons for cleared deforested wood, and does it get burned, does it get dumped, on like the fate of it, even qualitatively, that's where we're going to get improvements in reducing that spread. And soils in particular, because my understanding from looking last night at the inventories guidelines, it's completely different in terms of which soil carbon we look, how long does it carbon stay. I think an inventory is just 20 years. And we basically carry that carbon forever, as long as it warms, it's going to come out. So I think that's where some of that big negative things are coming out of our land models. That's where you guys don't see much. It's 0.9 kilograms of CO2, I think, for soils. And for us, it's much bigger, I think.
I'll just give a real quick answer, so I think we're close to time. So you asked about verification of models, and so I'd say one thing that all of the IAMs do is look, since we're thinking into the future, you don't have direct observations, but what you can do is compare trends you see in the future to comparable trends in the past, and I think all IAMs do that. Some of the IAMs, like the ones that Detlef and I work on, also run through the historical period, and there you can compare those results directly to observations. So the model I was working on, we compare land use and land cover change to the satellite record. We would compare land use change emissions to the Global Carbon Project and see how you line up with that.
Okay, Detlef, did you want to add anything to that? No. Detlef thinks Kate has done the job there. Look, we've run out of time, unfortunately, so we're going to need to bring it to a close here. But I think the last set of questions has just illustrated how important it is to have this communication between UNFCCC and IPCC on these matters. Some of these presentations have gone into a lot of scientific depth, and there's a lot of detailed understanding. But I think Giacomo's presentation at the beginning also shows the importance of digesting this down into messages that are simple to communicate, because people without scientific depth are actually very interested in these issues, and the communication, I think, is incredibly important. And just a couple of other things to finish off. This has been an unprecedentedly interdisciplinary cycle in IPCC with collaboration between the working groups. And it's really striking to get underneath this issue. We've had to put a panel together that has the task force on inventories, working group 1 and working group 3 all together to get a rounded picture of what's happening. So, and I think this is something that absolutely IPCC needs to build on in the future. And I think it was the last bullet on Eleanor's slide that said more communication between the modelling communities and the inventory communities. Can I just endorse that wholeheartedly? We need to do that. Sandro, you want to say one more thing?
IPCC has also tier 3 in the guidelines, which is models. So IPCC is not against, guidelines are not against models. Of course, the use of models then need verification according with the rules. But there are models also in the IPCC guidelines.
Yeah. So just say, let's draw it to a close here, and it may be that there's a need for some bilateral conversations between, say, UNFCCC and individual panelists, which I think would be a really good thing. But let's give a big round of applause to all the panelists. They've done a great job.